Hello people from the future, welcome to Normalized Nerd. In this video, I'm gonna be talking about linear regression and I'm gonna go really deeper into the concept. If you are new to my channel, then please subscribe to my channel. I make videos about machine learning and data science regularly. Well, I know that some of you are thinking that, hey, I have watched many videos about linear regression and I don't really want to watch another on the topic. But trust me, you will learn something from this video because there are much more to linear regression than just ordinary least square method, and I'm gonna go really deeper into all of the concepts and I'm gonna give you intuition why they came up. So let's start our journey by the good old ordinary least square method. So I'm not gonna really show you the basic. For that I have two videos actually, so you can just go and watch those videos about linear regression to get the basic concept of it, and then watch this video and you will understand everything. So in our ordinary least square method we have our model something like this. This is y hat and it is equal to beta 0 plus beta 1 x1 plus beta 2 x2. Needless to say that beta 0, beta 1 and beta 2 are my parameters, and this is bias, and these two are weights. Now throughout the video I'm gonna be referring the vector beta as our model parameter, alright? And when I talk about weights, please remember that I'm talking about only beta 1 and beta 2, and when I'm talking about bias I'm talking about only beta 0. Okay, got it? So this is our model, and to apply ordinary least square method we have to define a cost function, and I hope that many of you are familiar with the cost function, that is least square cost function, and the formula goes something like this: j of beta, and it is equal to 1 upon 2n. By the way, n is the number of data points in our data set, and the summation, and it runs from 1 to n for throughout the data points, and here we have ground truths minus our predictions, and obviously we have to square it because this is the least square cost function, and we minimize this term to get the values of beta. Okay, so I have drawn here a contour plot of this function, and you can see that I have drawn only the beta 1 and beta 2, that is the weights, and I have discarded the beta 0, that is the bias, because throughout the analysis I really don't need bias term. Okay, so here is the contour plot, and I hope you know that contour plot simply represents higher dimensional function into a lower dimensional plane. That is, here we have a 3D function represented in 2D plane, alright? And every point on this concentric circle corresponds to the same height. Okay, so we are good to go. And here I have pointed this particular point, which just represents the minima of this function. So after the minimization we will find the weights, that is beta 1 and beta 2 here. So in vector space we can just represent this two values using one point, alright? So imagine we are drawing a vector from here to here. So this if I just draw perpendicular here, so this is our beta 1, and if I draw perpendicular here, this is just beta 2. So that's how we represent a vector in vector space. So after the minimization our vector of weights beta will be this. So that was all about ordinary least square method, but here we have a huge disadvantage, and that is overfitting. Well, I'm not really gonna explain all the caveats of overfitting, but I'm just gonna give you the gist. Well, overfitting simply means our model has learned our training dataset so well that it fails to generalize on unseen data. Well, the main reason behind overfitting is that our model has learned tiny variations which are insignificant, but our model has learned the tiny variations in our training set. And this happens when some of the weights are very, very large compared to the others. In other words, when we assign too much importance to some features compared to the others, the model tends to overfit. Now, to tackle this problem, we have actually many methods available, but to show you the different kinds of linear regression, we just need to talk about only one method, that is the regularization. Now, to regularize our model, we just need to add one term to our cost function. This is our cost function, right? And by adding something with this, we will gonna get a new cost function, and that will be our new model. Well, what we should put here? There are actually two famous choices. The first one is adding the sum of the squares of the weights, and that is termed as ridge regression. And in the other case, we add the absolute values of our weights, okay, which is called as lasso. First, I'm gonna show you the cost function of ridge regression, and the cost function goes something like this. Don't focus on this plot now because I will explain it later. So here I'm just writing R as ridge. It is equal to, well, the same thing I have to write again, plus we are adding here beta j squared. Now notice here two things. The first one is we have another coefficient called lambda here, and we have started the summation from 1. But if you noticed here, there the beta starts from 0, but as I have told earlier that bias term is not going to be important in our analysis because overfitting happens mainly due to extraordinarily large values for the weights. So we just need to regularize our weights, not the bias term. That's why I have started this summation from 1, and m is just the dimension of beta. Alright, so here's the cost function of ridge regression, but this equation doesn't tell you much about this concept, and it doesn't really give you any intuition. Better if we can write it in some different format, and the format I am interested here is this equation is equivalent to minimizing our previous function with a additional constraint. And what is the constraint? Well, the constraint is simply the summation of beta j. I'm dropping the j and m here just for simplicity. Square must be lesser equal to some positive value r. Now it can be proved that for every lambda there exists a positive r. That's why this equation is equivalent to minimizing our previous equation under this constraint. Now focus on this plot. Well, this constraint can be visualized as a circle here. The center of that circle is the origin, alright? And previously the beta was converging at the minima of our contour of the cost function, but now the final value of beta we will get here because this constraint doesn't allow our beta to go outside of this red perimeter. Isn't it amazing that we can visualize this equation by this intuitive plot. I think it's amazing. And now you should be asking yourself, why does it prevent overfitting? If you look closely here, as we increase the value of beta j's, this term actually increase. But we have to minimize this term. So intuitively, we cannot increase our beta indefinitely. There must be a value after which we cannot increase our beta, and that's what the constraint is all about. The constraint is restricting the values of beta closer to the origin, and this means no feature will get too much importance than the other features. That's how we are tackling the problem of overfitting here. Now I'm gonna show you something called lasso regression. Well, here the regularization terms look something like this. I'm dropping this I and n here also. Squared plus, here comes lambda summation over the beta j's absolute value. Alright, we are not using the squared term here, but we are using the absolute value. And this is equivalent to minimizing our original least square cost function under the constraint summation of beta j's must be lesser equal to a positive number. And again, we can find an positive r for every value of lambda. And you guessed it right that this can be again intuitively explained by this plot. So this inequation can be represented by this square. And similar to the ridge regression, we cannot move our beta outside of the square. So here the final beta lies here. Now there's a very interesting thing about lasso regression, that is it can automatically select features. How does that happen? Suppose our contours look something like this. Let me draw another contour here. Forget about the previous contour, now focus on this contour. What will be the final result of beta here? Well, you can see that as beta cannot move outside of this red square, so the final value of beta should be this. Well, this simply means that we have beta r1 equal to 0. So we are automatically discarding the feature x1. Alright, and suppose we have 10 features. So we'll have a multi-dimensional diamond, and if our final value of beta falls on this axis, so we are just gonna neglect the other axis. So that's how lasso can be used as a automatic feature selection model. Now I would like to introduce some side notes here that might be helpful for some of you. Suppose we are increasing the value of lambda. What will be the effect on our cost function? Well, as we are increasing the value of lambda, we are constraining more and more on our beta j. So the bias in our model will increase, and our model will not learn the minute details in our training set. So ultimately it will result in underfitting. And what if we just use a lower value of lambda? Well, if we just decrease the lambda, then we are actually reducing our constraint, and it will tend to learn the minute details in our data set. Alright, what if we put lambda equal to 0? Well, if we put lambda equal to 0 in either lasso or in ridge, we will find just our ordinary least square method. Alright, and I can't just tell you the correct value of lambda for your model because it depends on the dataset. So you have to find the correct value of lambda for your own problem. And generally it lies between point 1 to 0.0001. So was that it? Have we just covered every possible linear regression model? Well, not quite yet. What if we want to use something different in place of this term? You can see that in these three models, we are just using this difference between ground truth and the prediction value as our error. And this is called residual and we are just squaring them. What if we want to use some different kind of residual? Now, why would anyone want to do that? I'm gonna explain that towards the end of this video, but for now, let's explore what are the different possibilities for our residuals. First, I'm gonna show you something called major axis regression or orthogonal regression. This is the thing, and here we consider the squared distance between the ground truths to the best fit line as our residual. And here you can see that this is our ground truth point and we have drawn a perpendicular to the best fit line, and obviously this angle is 90 degree, and this line, the length of this line is d, and we are squaring this, and by Pythagorean theorem we can easily find this, and we minimize this d square. So instead of minimizing this term, we minimize the d squared term. Now, just to give you a sense how it is different from our above three methods, look at these two plots. Well, this is the most common plot, I think, and you see here that this distance is just yi minus yi pred, which simply means the difference between ground truths and the predicted values, and this term is actually same as this. However, we could have also done like this. Here we are considering the error along x-axis, but here we were considering the error along y-axis. But in this case, we are considering the error that is in the perpendicular direction. So, in a sense, in this orthogonal regression, we are actually considering the errors in both the directions. You can just look at the formula here and you can just notice it that we have both x term and y term. And by the way, this capital Xi and capital Yi are just the foot of the perpendicular. Alright. Now there's another variation of this which is known as reduced major axis regression. Well, this concept is very similar to the above one. The difference here is instead of calculating the d square, we are just calculating the area extended by these 2 points. So to find the area, we just need to calculate the area of the rectangle, which can be easily found by multiplying the x error and y error. Just to be clear here, what we are minimizing in reduced major axis and major axis regression is that in case of the major axis regression, we were actually minimizing the summation of di's, okay, and the constraint in this minimization was our model. And let me just write the model here. For convenience, I am working with only two variables, okay. So the model is yi is equal to beta 0 plus beta 1 x, okay. And if I just change the side here, you will notice that I will get yi minus beta 0 minus beta 1 xi equal to 0. So the major axis regression is equivalent to saying that we are minimizing this term under the constraint this equation. Alright. And in case of the reduced major axis regression, we are minimizing this thing under the constraint of this equation. So this is our minimization objective and this is our constraint. Okay, so now I'm gonna answer why would anybody want to use this orthogonal distance instead of this horizontal and vertical distances. Well, the main concept of this kind of error is that to incorporate both the uncertainties in y-axis and x-axis in our model. In other words, it may happen that in our data we have uncertainties corresponding to both the independent variable, that is our x, and in the dependent variable, that is our y. So to incorporate the errors, the uncertainties for both of them, we need to consider error in both the directions, and that is what we have done in orthogonal regression and reduced major axis regression. And I would also like to mention one interesting difference between this orthogonal regression and our previous methods is that in our previous method, like Ridge, Lasso or OLS, if we would have considered y errors and x errors differently, then we would have got two different regression lines. That is actually makes sense because in one case we are actually minimizing the y errors, but in other case we are actually minimizing the x errors. But in our orthogonal regression and our reduced major axis regression, as we are considering errors for both the axes, we would always get one single regression line. That means it preserves the symmetry between x errors and y errors. So if you are trying to build a model which is symmetric with respect to your y error and x error, then you should probably go for reduced major axis or major axis regression. So that was all for this video, guys. I hope that now you're comfortable with the concept of linear regression and its different variants. If you have liked this video, please share this video and subscribe to my channel. And thanks for watching.